Hello. In this video, I'm going to explain when a function has an inverse. Before that, we need to understand the concept of a function. Not every mapping is a function. A mapping from a set x to y, and the mapping is denoted by f, is a function if it is well defined. Well defined means that the definition makes sense. For example, this is an x set, this is an y set. If you have an element in x set which is not defined by f, that doesn't make sense. If f is not defined for all x's, it doesn't make sense. Also, if you have an element in x, x1 is equal to x2, one element in x, but it goes to two different elements in y, that doesn't make sense either, because you're defining one x in two different ways. It doesn't make sense. So if f defines an element in two ways, it doesn't make sense. So mathematically, these two we can express with these two conditions. A map is well defined if for all x, fx is equal to fy. This one corresponds to the first case, and the x1 is equal to, if x1 is equal to x2, this implies fx1 has to be fx2. So this corresponds to the second case. If you have a function, then a function is one-to-one if it satisfies this condition. What it means. So you have fx1 is equal to fx2. This condition should imply x1 is equal to x2. In our particular case, we assume that the y is in a range of f. So every element in y has an preimage. So if you have a point here in y, it cannot go back to the two different elements. This is allowed as a function. See, x1 and x2 could be different, and it may go to the one element in the definition of a function. But this is not allowed for one-to-one functions. Two different elements cannot go to the one element. So every single element in x should go to one y. If this is the case, the function is called one-to-one. For example, f from real numbers to the real numbers, fx is equal to x squared, is not a one-to-one function. This is an x-axis, this is a y-axis, this is y squared, y is equal to x squared graph. And if you look at the f minus 1 will be 1, and f1 will be 1, so you have for minus 1 and 1, you have one entry in y, and this case would occur, and it does not allow it. So this function is not one-to-one, but if you think of this side, or if you think this side, they are one-to-one functions. For all x in this range, we have one y, and similarly here as well. For each x here, we have one y. I think that makes it clear what is a one-to-one function is. Now, this is an important fact. Well, basically, this is the definition of an inverse function. Assume f is a function from x to y, and we assume that the y is a range of f, so none of the y elements is be left over. All has a preimage. If f is a map from x to y is one-to-one, then there exists a function from y to x such that f composite g is the identity of y, g composite f is the identity of x. So this is the identity map on x, this is identity map on y, which means that every element goes to itself. That's definition of an identity map. So schematically, what this and this condition represents are those ones. So if you apply the first f map, then the g map, so this is g of f, should give you the identity on x. If you apply the first g map, then f map, then that should give you the identity on y. If this function g, if f is one-to-one, it exists, right? This is a one thing. So then G is called the inverse of a function and is denoted by F inverse. So the existence of the inverse of the function is 1-to-1. And also y needs to be in the range of f. These are the conditions for f to have an inverse. Let's have an example. F is defined from 0 to the infinity to the 0 to infinity by fx is equal to x squared, a very simple example. And the inverse is from this set to this set now is given by the fx is equal to square root of x. To see that f inverse is really the inverse of f, we need to prove these equalities. F of f inverse or f, which is the composites, needs to give us the identity. So it's a pretty straightforward to prove it. Now let any x in the 0 to infinity, f composite f inverse x is f. So f inverse x defined as a root x, then f will be the square of this, then we will obtain x. Here we have f inverse x squared, and then when we're taking a square root, then it will get us. This is a positive because x is in the 0 infinite range. If it is negative, if it's from minus infinity to 0 infinity, you need to think about square roots as minus and so on. So this gives us the identity map. This composites gives us the identity map on 0 infinity. So schematically, this is the f function graph, and this is the f inverse function graph. This is a reflection based on the y is equal to x line, as you see here and here. If you think about this one as a sheet and fold it along to the x is equal to y line, this graph and this graph matches. If you wish to see another example of this subject, please also watch the video called Example of the Inverse Function, CH6 2b. Thank you very much.